Welcome to our continuing discussion on transport in one dimension. We had gone through the separation of variables procedure for transport in a finite domain in the previous two lectures. This is an important procedure, and therefore, I will try to summarize this in this lecture before proceeding to the next topic. Okay. What we had was transport in a finite channel, okay, of cross sectional distance L. The top surface was at temperature T infinity, the bottom surface at temperature T naught. Okay. So, therefore, if I consider this as the z coordinate, the boundary condition was that at T equals T naught and z equals 1, T equals T infinity. Okay. We have defined scale distances, z star is equal to z by L, T star is equal to T minus T infinity by T naught minus T infinity. Okay. And in those coordinates, z star is equal to 0, T star is equal to 1, z star is equal to 1, T star is equal to 0. Okay. And at time t is equal to 0, we had t is equal to T infinity for all z greater than 0, okay, because at time t is equal to 0 is when we had switched on the heating. Okay. At that point, t was equal to T infinity throughout the domain, only the surface was heated. Okay. So, what that implied was that T star is equal to 0, T star is equal to 0 for z star is equal to 0, okay, where the scale time was equal to T alpha by L square. Okay. So, that was the scale time in the problem. Now, the equation that I was trying to solve was the convection, the diffusion equation, which basically reduced to partial T by partial T is equal to partial square T by partial z star square. Okay. Now, this equation I had expected that in the long time limit you would get a steady temperature profile. Okay. In the long time limit you would get a steady temperature profile. That temperature profile was satisfying the equation, okay, because in the long time limit the temperature should no longer depend upon time, it should attain a steady value in the long time limit, and that gave us the steady temperature is equal to 1 minus z star in this case, a linear temperature profile. Okay. That was the final solution in the case of steady state in the long time limit. And then we had expressed the temperature as the sum of the steady part plus the transient part. Okay. And if you look at these boundary conditions here, okay, if you look at these boundary conditions here, at z is equal to 0, T star was equal to 1. Okay. The steady temperature is also equal to 1, okay, which implied that the transient temperature was equal to 0. Okay. At z is equal to 1, T was equal to 0, the steady temperature was also equal to 0, which implied that the transient temperature is equal to 0, okay, for the transient temperature field. Okay. And at time t is equal to 0, the total temperature was 0, the steady temperature is equal to 1 minus z star. So, the steady part plus the transient part has to sum to 0. Therefore, this implies that the transient temperature was equal to minus of 1 minus z star. Okay. So, we have already solved for the steady part. The transient part is a part that goes to 0 in the long time limit, because the temperature has to tend to the steady part. So, that transient temperature goes to 0 in the long time limit. It is important to note that it is also 0 on both boundaries. Okay, it is also 0 on both boundaries, and it is non-zero only within at the initial time. Okay, it is non-zero at the initial time, and then it slowly decreases to 0. Okay. So, as I said, okay, my steady temperature profile looks like this, okay, and my initial temperature profile looks like this. Okay. So, what I have done is effectively to write this as the sum of a steady part, okay, sum of a steady part plus another part which is the transient part. Okay. That transient part is basically equal to 0 in the long time limit. Okay. So, that if I sum the steady part plus the transient part, okay, in the long time limit, I will get the total temperature. Okay. Initially also the sum has to be equal to 0, and therefore, the transient part at t is equal to 0 has to look something like this. Okay. Okay. Whereas, the transient part in the limit as t goes to infinity has got to be equal to 0, so that the temperature reduces to the steady part. Okay. So, that is basically the problem that we were trying to solve. We had already got the steady part, we wanted to solve for the transient part. Okay. So, the equation that we had was partial t transient by partial t is equal to partial square t transient by partial z star square. Okay, that was the equation that we had. We had to solve it subject to the condition that t transient is equal to 0 at z star is equal to 0 at z star is equal to 1, and t transient is equal to minus of 1 minus z star at t star is equal to 0 for z star greater than 0. Okay. That was what we were trying to solve. Note that this direction, the z direction, is the homogeneous direction. Okay. The temperature is equal to 0 on both boundaries. So, z, as far as the transient temperature is concerned, the z direction is the homogeneous direction. The boundary condition is that the temperature is 0 on both boundaries. The time direction is the inhomogeneous direction, because I have an initial condition at which T t is non-zero, okay, and then it decays to 0 as time progresses. So, the time dimension is the inhomogeneous dimension in this case. Okay. The way we had solved it was to write T t is equal to some function of t, some function of z. Okay, we had written it as a function of t and a function of z, and using separation of variables we got an equation of the form 1 by f of t df by dt 1 by z of z d square z by dz square. That was the equation that I had got, and both of these sides, they have to be equal. The left side is only a function of time, the right side is only a function of z. These will be equal only if both are constants, okay, because if both are not simultaneously constants, if I keep time a constant and change z, then the left side does not change, the right side changes, and vice versa. Okay. So, both of these have to be constants. What constants should they be? Okay. If the constant were positive, this function f would be an exponentially increasing function in time. Okay. If the constant were positive, this function f would be an exponentially increasing function in time. That does not satisfy our expectation that in the long time limit, T star has to go to 0, the transient part has to decrease to 0. That cannot happen if the temporal variation is an exponentially increasing function. So, the only possibility in that case is for the temporal variation to be an exponentially decreasing function, which means that the constant is negative. Okay. I had also showed you last time that when the constant is positive, the function z admits only trivial solutions. If you write it as an exponential function, exponentially growing and decaying, both of those constants in that equation are identically equal to 0, and you just get a trivial solution, capital Z is equal to 0. You get a non-trivial solution only if the constant is negative and this is equal to you get a non-trivial solution only if this is negative and it's equal to minus of n pi the whole square, where n is an integer. Okay. In that case, the non-trivial solution for z is a sine of n pi z star. The non-trivial solution for t is equal to e power minus n pi the whole square t star. Okay. Only then do you get a non-trivial solution. And the special form of this constant, if you recall, was fixed from the requirement that you should have homogeneous boundary conditions. Only for specific values of this constant, only if this constant is an integer times pi, does the solution for the function z satisfy the homogeneous boundary condition that it has to be 0 on both walls. So, therefore, the fact that you have a homogeneous boundary condition in one direction fixes the value of this constant and fixes the value of the function. These have to be sine functions. So, the total equation for the temperature was of the form that was the total equation for the temperature, and these coefficients now had to be evaluated from this initial condition. These coefficients had to be evaluated from this initial condition. And how did we evaluate it? Using what are called orthogonality relations. For these functions which are called eigenfunctions, for these functions in the homogeneous direction which are called eigenfunctions. So, those orthogonality relations were of the form integral dz star from 0 to 1 of sine n pi z star sine m pi z star is equal to delta n m by 2. Where delta n m is 1 if n is equal to m and is equal to 0 if n is not equal to m. So, that was the procedure that we had used, and we had finally got the solution for the temperature field. The temperature it consists of the steady part 1 minus z plus the transient part. The constant was minus 2 by n pi sine n pi z e power, let me write that below. So, that was the final solution that we got. There are some important intermediate steps that need to be kept in mind whenever you do a separation of variables solution. you have to first identify the homogeneous and the inhomogeneous direction. That is the reason that we had separated out the solution into a steady part plus a transient part, okay? Because the total temperature field and the steady temperature field satisfy the same boundary conditions. Therefore, the transient temperature field has to be equal to 0 on both boundaries. So, that is the homogeneous direction. Okay. The inhomogeneity is coming in at the initial time. Okay. You could have problems where you have one spatial homogeneous direction and one spatial inhomogeneous direction. In any case, you have to reduce the problem in such a way that the boundary conditions are all homogeneous in all directions except one, and that one direction is the forcing direction. Okay. For the homogeneous directions, the boundary conditions are all 0, either the temperature or the flux, whatever it may be. Those boundary conditions are all 0 in all the homogeneous directions. Okay. The fact that you have boundary conditions equal to 0 implies that the solutions have to be of a special form. Okay. As I showed you in the earlier lecture, if I just assume a positive constant for the separation of variables procedure, okay, if I assume a positive constant over here, I do not get a non-trivial solution. The solution just tells me that the entire function has to be 0 everywhere. Even if I assume a negative constant, if I did not assume a specific form of this constant as an integer, the solution would tell me that the solution has to be 0 everywhere. It is only for specific values of this constant that the solution is non-zero. Okay. Those are a finite set. Okay. I mean, they have to be a discrete set of values. Okay. They cannot be just a continuous variation in values, it has to be only for a discrete set of values. In this particular case, it is an infinite set, n can go from 1 to infinity, but it is still a discrete set. Okay. N can have only integer values. These are the eigen values, and the functions, the functions here are what are called the eigen functions. For these eigen functions with homogeneous boundary conditions, you can show that there do exist orthogonality relations. That is the subject of applied mathematics, which I will not be able to get into in this course, but you can actually show that these orthogonality relations apply. Okay. So, therefore, even though I had an infinite set of constants, I can evaluate each one of them, because each constant is orthogonal to every other constant. Okay. I am sorry, each function is orthogonal to every other function. Okay. So, it is like if I had a vector field, okay, let us say that the vector A, okay, I will put it with an underbar. Okay. I can write it in terms of Ax, Ex plus Ay, Ey plus Az, Ez, okay, in some 3-dimensional coordinate system. A is a vector, okay, in a 3-dimensional coordinate system. Okay. Now, I can get each of these constants Ax, Ay and Az, okay, by dotting A with Ex. Okay, if I take the dot product of A and Ex, I will get the component Ax. Okay, if I take the dot product of A dot Ey, I will get the component Ay. Okay, similarly, if I take the dot product of A dot Ez, I will get the component Az. Okay. The reason I get this is because these vectors are orthogonal. I know that Ex dot Ey is equal to 0. Okay. Ex dot Ez is equal to 0, okay, and Ey dot Ez is equal to 0. So, they do form an orthogonal coordinate system. Okay. They are perpendicular to each other, Ex, Ey, Ez. Okay. They are all perpendicular to each other. So, if I dot any two of them, I will get 0. I could not have derived this. Okay. I could not have derived this if I had used a coordinate system in which the vectors were not orthogonal to each other. Okay. If I had used a coordinate system in which the vectors were not orthogonal to each other, in which they were not perpendicular to each other, I could not have got this. So, that is the importance of orthogonality relations in vectors. Okay. Okay. Similar applies in this case, except that it is an infinite series of functions. I had z of z star okay, or rather the transient temperature. Okay. So, let me see, this was just a transient temperature at t equals 0. Okay. Okay, is equal to this function. Okay. I can write this as the summation of a n times S n, okay, where S n is equal to a function sin n pi z. Okay. Now, these functions satisfy orthogonality relations in the sense that the product of S n and S m, okay, if I define this product of S n and S m as integral 0 to 1 d z star, okay, S n of z star S m of z star. Okay. If I define this as the product of these two, this is equal to 0 for n is not equal to m and is equal to 1. In this case, it is 1 by 2. Okay. Okay. So, this thing in the case of these functions is the equivalent of the dot product in the case of vectors. Okay. So, since the product of two functions is equal to 0 if n is not equal to m, right, I can quite easily invert this equation here. Okay. I know that at t star is equal to 0, right, I know that summation a n S n is equal to minus of 1 minus z star. Okay. If I take this inner product on both sides with respect to m, where the inner product is defined in this manner, then I will get sigma a n S n comma S m is equal to minus the inner product of 1 minus z star comma S m. Okay. Similar to what I am doing over here. Okay. I am taking the inner product of this with some unit vector. Okay. Similarly, this with some function. Okay. This inner product only gives me a m. Okay. So, this gives me basically summation of a n times delta m n by 2, n is equal to 1 to infinity, is equal to minus of 1 minus z star comma S m. Okay. And since delta n m is non-zero only when n is equal to m, this reduces quite easily. Okay. This just gives me a m by 2 is equal to okay. So, that is the conceptual underpinning behind writing these in terms of these basis functions, okay, the eigenfunctions of the basis functions. Since we know that they are orthogonal, we can determine each coefficient. On the other hand, if we had taken some other function which was not orthogonal, similar to some other set of vectors which was not orthogonal, we could not have got each one of these individually. Okay. In the case of vectors, there are only 3 relations you will get, therefore, you can invert it to get 3 constants a x, a y and a z. In this case, there are an infinite number, okay, and so therefore, you cannot invert it quite simply. Okay. Essentially, what we are doing is we know that at time t is equal to 0, okay, at time t is equal to 0, the total temperature is 0. Okay. The steady temperature is given by this function. Okay. The steady temperature plus the transient temperature has to sum to 0. Therefore, the transient temperature looks something like this. Okay. The sum of these two will be equal to 0. Okay. So, if I plot this transient temperature, if I take this z star coordinate, okay, as a function of z star, I plot the transient temperature. Okay. Z star goes from 0 to 1. Okay. If I plot t star of z star, okay, I get a function that is it should actually be negative in this case. So, let me okay, I get a function that looks something like this, okay, for the transient part of the temperature. Okay. I get a function that looks something like this. Okay. Note that this is 0 over here as well. Okay. The reason is because you just increased the temperature. So, both the steady and the total temperature field are equal to 1 at this point. So, the transient part is actually equal to 0 at z star is equal to 0. So, it is a sharply varying function that looks something like this. Okay. It is equal to 0 at z star is equal to 0, but it has this linear function for any z star not equal to 0. Okay. What you are doing is to express this function as the sum of sine functions. Okay. This is one function for n is equal to 1. This is a function for n is equal to 2. Okay. So, for n is equal to 3 it will look something like this, and so on. Okay. So, expressing this function that I had here, okay, as a sum of sine functions, each of which goes to 0 on both boundaries. Okay. So, you take each of these sine functions, okay, t of okay. I am writing this as the function as the sum of a n times sine of n pi z star. Okay. So, I am multiplying each of these functions, okay, by a constant, each of these functions, there is an infinite number of them, okay, by some constants, so that when I add them all up, I end up with the function that I had, okay, and from that I can evaluate these constants. Okay. Each of these functions decays at its own rate. Okay. So, for n is equal to 1, the function will be of the form sine pi z star e power minus pi square t star, n is equal to 1, okay, n pi the whole square times t star. So, it is of the form sine of pi z star times e power n pi t star times a 1. For n is equal to 2, it is a 2 sine 2 pi z star e power minus 2 pi the whole square t star. Okay. So, once this initial shape I have decomposed into each of these sine functions, each of these decays at its own rate. Okay. For n is equal to 3, you will get a 3 sine 3 pi z star e power minus 3 pi the whole square t star, okay, and so on. Okay. You will get higher and higher term, and each of these functions decays at its own rate. Okay. So, once from the initial shape of the function I have got all these constants, okay, I can multiply each of those functions by their own natural decay rate, add them all up, and I will get the solution at any instant of time. Okay. So, that is the basic principle. Okay. I am basically expanding this initial perturbation in a series of orthogonal functions. In this case, the natural orthogonal function is the sine function with integer n. Each of these decays at its own individual rate, and therefore, I can, from the construction of the solution, I can get what is the temperature at any time. Is equal to sigma a n okay. And you can see that for higher and higher n, these functions decay faster and faster. Okay. So, functions with n higher, so for example, function with n is equal to 2 decays as e power minus 4 pi square t star, which is much faster than e power minus pi square t star. So, the lower functions actually decay much slower. The higher functions for higher n, they decay much faster. Okay. So, if you are interested in only some particular resolution in the solution, and if time is larger than 1, you are guaranteed that you can truncate the series at a finite set of terms, okay, in this series, and neglect all the higher order terms, okay, because these higher functions decay much faster than the lower functions. Okay. So, in that sense you can get an approximate solution for this problem. There will be other problems in different configurations in which similar procedures will apply. Separation of variables, you have to identify homogeneous boundary conditions in all directions except one. In those homogeneous directions, you have discrete solutions, discrete eigenvalues and orthogonal eigenfunctions. Write the inhomogeneous part in terms of those orthogonal eigenfunctions using orthogonality and calculate the coefficients in those. Once you have those coefficients, you can construct the entire solution as the sum of each of those orthogonal functions, and you are guaranteed that any function can be written in this as the sum of these orthogonal functions, because this function space is complete and orthogonal. Okay. So, that is the procedure that is used for solving problems by separation of variables. Okay. We will see that in different configurations as we go along in the course. So, next I would like to take up balance laws in cylindrical coordinates. The problems that we have solved so far are in what are called a Cartesian coordinate system. Okay. Two surfaces with the coordinate perpendicular to the surface. Okay. And therefore, we could write the two surfaces as z is equal to 0 and z is equal to L. Okay. And then we could write a differential balance, okay, for a small interval delta z, and then solve the problem within that small interval. Okay. What if you are doing a solution to a problem in a cylinder, for example? We often see these flows in pipes, okay, for example. These are all in cylinders, okay, and in that case the configuration has a cylindrical geometry. Okay. If I plot the cross section, it looks like a circle. Okay. Now, one could of course use a Cartesian coordinate system, okay, and write down balance laws in this Cartesian coordinate system and try to solve it. Okay. However, in a Cartesian coordinate system, the way that I would have to describe this surface of the cylinder, okay, if I had, let us say, orthogonal coordinates x and y, would be to say that x square plus y square is equal to r square. Okay. And then applying boundary conditions at the surface will become problematic, because when expressed in terms of x and y, I do not have boundaries at specific values of x and specific values of y. Rather, I have some inconvenient combination of x and y. Okay. It would be much easier if I could choose a coordinate which is parallel to the bounding surfaces. Okay. It would be convenient if I could have a coordinate which is parallel to the surface bounding this geometry. Okay. In other words, this surface, okay, going around should correspond to a surface of constant coordinate. Okay. In that case, specifying the boundary conditions becomes much simpler. Okay. However, specifying the balance equations becomes a little more complicated. And so, I will talk about cylindrical coordinates. I will start that in the next lecture, and we will see how to solve problems in cylindrical coordinates. Okay. So, that is the program for the next series of lectures. In Cartesian coordinates, I have shown you two different ways of solving problems. One is the similarity solutions when there is a deficit of dimensions. The second is the separation of variables. There is a third class of solutions for oscillatory flows, which I have not yet covered. We will see that as we go further in the context of pipe flows and so on. Okay. But these two procedures, once again, I will first frame equations in coordinate systems which are not Cartesian, and then go through how these are solved. So, we will continue with cylindrical coordinates in the next lecture. We will see you then.